Hello guys, in today's video I want to cover some of the basics maths for Pytorch. This is a follow-up to the course series on Udacity. Uh, so the first topic that I want to cover is, what is differentiation and why is it so important in deep learning? And also, I will teach you how to differentiate. Now, I've been teaching calculus for about 2 years, 2.5 years, and I've developed a system where people can just use that system and just, if you follow it, and pretty much 95% of the time you'll find the derivatives of certain function. So that will lead to my second topic, which is the derivative of the sigmoid function. Um, just to recall your memory, the sigmoid function takes in the score of a particular perceptron and then converts it into a probability distribution. Okay, so which is a very important concept, and also I guess it will let you guys see how the excuse me, how the map system can be used to derive something like this. It is very easy. Okay, now the third one is the chain rule. The chain rule is really important, not just to deep learning, but to just physics in general. Okay, matrix multiplication. As you guys are well aware, matrix multiplication, they pop up everywhere in deep learning, especially I guess in MLPs, in the first, I don't know, 10 to 20 videos in the Pytorch series. So I will cover those. And then gradients and slopes. Gradients and slopes kind of the same as the first line item. And then finally, the cross entropy. Now, I found cross entropy to be very confusing at first, but I found a way to explain it to myself and understood it. Okay, so now what is differentiation? Okay, now differentiation is all about finding rates of stuff. Okay, so for instance, if you have a car that is driving at 50 miles per hour, 50 miles per hour is a rate. It's a derivative of acceleration, right? Well, many people might not know what that means, but there is a lot of reasons why you want to learn, basic differentiation. So, uh, so here is where is it? So here is the map system that I've developed. So basically, differentiation functions can be broken down into 4 types. So you got polynomials, exponentials, logarithmic, trigonometric. I believe I pronounced that right. Trigonometric. So here is the original form of a particular function, right? So if you look at polynomial, you'll see f of x. Now, f of x. Now, what does that mean? F of x. F of x just basically means that x is the variable of the equation, right? So if I write this, right, if I say to you that I just move this to the side, so I have more room to write on. Let's have a look. Okay, so if I say to you that f of x is equals to maybe, I don't know, x squared plus 2 or something like that. What this means is that this function of f, okay, function of f is dependent upon a variable called x, right? Now, the reason why I stress this is because notation is very important in calculus, okay? So if I have something like, f of x is equals to x squared plus k, Well, now what is k? Now, if f of x, if they present the equation like this, f of x is equals to x squared plus k, that means k is a constant. It's a constant. Okay, now it's very critical piece of information because it goes into your derivatives, right? Constants, if you differentiate a constant, that constant will become a 1, okay? So let's go back to this. So you got f of x equals to gx to the power of n, right? Now gx is just like any other function that depends on x, right? Now if you look at to the other side, now you have this thing called f prime x. Now what does f prime mean? F prime is just means the first derivative, okay? So if you have two dashes, that means it's a second prime. Now what is a second prime? Second prime is just basically mean that this function derived twice, okay? So the first derivative of gx to the n is equals to this junk right here. Now it might be, now to people who know a little bit of calculus, they might be confused to what that really is. But if you just break it down, it's just simply taking the power. You take the power, you bring this thing down, right? You bring it down, and you minus 1, right? So for instance, if you go back, let me rub all of this out. Eraser. Come on. Oh, it's not working for some reason. Okay. Right, there we go. There we go. So for instance, if you have a function f of x is equals to x squared. Now if you just simply look at this equation, you know, let's write it down, right? So f of x, f prime x, sorry, is equals to n dot, no, dot just means multiply, okay? So g of x minus 1 multiply by the derivative of gx. Now it might look, you know, it might look more complicated than it really should be, but trust me, this thing works. So the f prime of x, right, will be equals to, you bring this power down, which is 2x, you minus 1 from that, which is 1, you multiply by this right here. So this is gx right here. So gx, so a variable standing by itself, if you differentiate that, that would just becomes 1, okay? I think I made a mistake a couple of minutes ago where I said that constant of, for example, k, if you derive that, that will actually become 0, okay? So apologies. So now if you look at the exponentials, the f of x equals to f of x is equals to exponential to the g of x. Now g of x, now you guys might be confused what's g of x. G of x can be anything, right? It can be, I don't know, like x squared plus I don't know, like x plus 1. You know, it could be anything. It could be sine to the x, or it could be what else? What's complicated? Like maybe a tan of x. I don't know. It could be anything, right? So all I'm saying is that if you have an exponential raised to the power of something, right? Just something, that derivative of that whole equation is given by this. It's given by the derivative of whatever that function is multiply the original function, right? So let's do an example, right? So let's say I have, let's do a, my computer is kind of slow, guys, so my pad is not really real time. It's not really reacting to the way I write. So anyway, so you have, let's write this down, right? So g of x, whoops, sorry, not g of x, f of x. So you got f of x is equals to e, let's say, I don't know, like x squared plus x plus 1, right? It could be anything, guys. So the derivative, now let's write the map system down. So derivative of fx, which is f prime x, is equals to g prime of x multiplied by g of x. Oh no, sorry, excuse me. It's multiplied by the original function, right? Which is the e to the g of x. Now, what is the g of x here? Now, the g of x will be x squared plus x plus 1. Now, if you derive that, which means you take the derivative, what would this be? So if you follow it back to the derivative function, you will see that, oh, this is actually 2x. It's fairly simple. What is x? X derivative in respect to x, that will be equals to 1. Okay, so that's your g prime of x. So all you gotta do is just plug it back. So f of x is equals to, put a bracket in, so 2x plus 1, okay, multiplied by the e of x squared plus x plus 1. Simple as that. Now, now this identity or this derivative is used to derive the sigmoid function, right? Because sigmoid function is basically they are just exponentials, right? But it's not as simple as this, right? Well, it is simple, but the simplification part after the derivative, I would say that's the hard part to digest. So let's look at another example. So you have f of x equals to the natural log of a certain function, right? So let's write this down. So you got f of x is equals to natural log of, I don't know, maybe let's try this one, right? So let's go back and plug this in. So plus x plus 1. Okay, now this might look a little bit complicated, but if you just look back to the derived function or the mapped function, what you'll find is that, oh, actually it's not that bad. So what is okay? So the f prime of x is equals to no, sorry. Let me go back. So let me write down a general formula for the natural log. So f of x, wow, man, I can't write today. Come on. Okay, so if you get f of x is equals to natural log of g of x. Now, remember, g of x can be anything, guys. So the derivative of that would be the g prime x over g. Okay, over g. So if you just take this, right? Now, what is my g of x here? G of x is e to the x squared plus 1 x squared plus x, excuse me, plus 1. Okay, now what is the g prime of that? Well, we just solved it. G prime of x is that. So all we gotta do is plug this in, so 2x plus 1 e to the x squared plus x plus 1, open parentheses, close parentheses. Okay, so we are halfway there already. So f prime of x is equals to all of that. So x squared plus 1 e to the x squared plus x plus 1 over, what's g of x? G of x is just that. So e x squared plus x plus 1. See? Very simple. Very simple. Don't let, just because it looks complicated doesn't mean it's complicated to derive. Okay. Now it's the same logic as these ones as well. Okay. And I have a list of explanations that you guys can follow along. I will link this to when I upload this video on Slack as well as on YouTube. I will copy this document along with it. Okay, so you guys can follow along, and if you guys have any information, questions, please feel free to reach out. Okay, cool. Now I hope that is somewhat useful. These will serve you very well on your journey to learning deep learning. Deep learning has a lot of maths involved, and when people say to you that, oh, you don't really need to know a lot of math, well, I mean, you don't really need to know, because there are a lot of libraries such as Pytorch and TensorFlow. So all you really need to do is just know the top level stuff of how things work, and that's it. But to be honest, you really need to know basics of calculus in general, because they are very useful. Okay, so let's move on to our next topic, which is the derivative of the sigmoid function. Okay, this is going to be fun. Okay, so what is a sigmoid function? Now, the sigmoid function is given by sigma of x is equals to, okay, remember, right, 1 over 1 plus e to the negative x. Okay, it's fairly simple. Now, some of you may or may not know this, but you can actually write something like 1 over x into an index form. Okay, now index form is just basically taking this and turn it into some sort of a power form. Okay, so you got x to the negative 1. Okay, so if you have, for instance, if you have 1 over x cubed, right? You can index that into x to the negative cube, right? So if you have, I don't know, 1 over x plus 1 or something, that becomes x plus 1 to the negative 1. Okay, so basically take whatever you have, and if you want to put it up, well, not put it up, it's not a technical term, but if you want to get rid of the quotients, right? If you want to move the quotients into a fraction form, then this is what you can do. You basically take whatever that's at the bottom and you multiply the power by a negative 1. Okay, so this is a technique at which we can use to derive the sigmoid function. Okay, so let's see. So this is our equation right here. Okay, so if we're going to index that, that will become what? That will become 1 plus e to the negative x to the negative 1. Okay, now what does this look like to you? This look like a polynomial type question, right? Where you have the g of x, and you have a power, right, raised to the n. So what is my gx here? My gx is 1 plus e to the negative x. right? So if I do the derivative of that, that will become what? Excuse me. That will become now a constant as in any other value. The derivative is always 0. Okay, so 0 plus, well, what is n here? N is x, right? So negative x, if you differentiate that, that will become -1. Okay, so -1 multiplied by the original value, which is that. So the g of x, sorry, g prime x is equal to negative e to negative x. Okay, now let's go back to this. So I'm running out of space, but anyway, so let me write down the equation again. Now by doing this, we're already halfway there. So let's write down the mapped version, which is, okay, f of x is equals to g of x to the power of n, right? So the prime function, the prime version of that is equals to n multiply by g of x multiply, and n minus 1, and then multiply by g prime x. Okay, so in this case, here's my function. What will that be? That will just be, excuse me, -1 multiply by g of x, which is just that, plus e to negative x, and then -1, so -1 minus 1, that's -2, and then multiply by, what's g of x? G of x is negative e to the negative x. Okay, so you have negative, here, they cancel out. Yay. So you got, so e to the negative x divided by, so here you have a negative, right? But you can also, what you can also do is turn it back into a fraction form. So you get 1 plus e to the negative x, right? So hope I have enough room. Let me just make a boundary for myself here. Okay, so here's what we have. Here's what we arrived to. Okay, now what can we do from here on out? So what we can do is that we can simplify that. Now, what we can do here is that say, hey, maybe we can do this, right? So e to the negative x, I can say, hey, if I plus 1 and minus 1 from it, something tricky, so that alone, plus 1 and minus 1, that is basically saying plus 0. Okay, so I'm not trying to add anything to it. I'm just trying to manipulate what I have here, so I can simplify this formula, this equation, even further. Okay, so what I can do here is, now since that I have what you would call it, so right now, here's what I got. Okay, so what I can do is e to the negative x plus 1 over 1 plus e to the negative x squared minus, right? This is basic fraction, I don't know what you call it, but it's just basically, it's dividing out what I have, right? So all of this, that becomes 1, and that, sorry, don't need to do that. Let's see, cross that out, great. That becomes 1, right? So now what do I have left? I have, so let's write this all out again. 1 and then squared. That doesn't look right to me. Oh, I know why. And then minus 1 over 1 plus e to negative x squared. Okay, so now what I can do is that I can factor out the common denominator, right? So 1 plus e to negative x is equals to 1 minus 1 over 1 plus e to the negative x, right? Because if you multiply this back in again, you'll have this, right? So you might look at this and you say, hey, this look familiar. Well, this is actually a sigmoid function. So sigmoid of x is equals to 1 minus the sigmoid of x. Okay, so that's how we arrive to it. So basically, in general, the sigmoid function, if you look at the map system that I've developed, involves the polynomial type mapping and the exponential type mapping. So you can use the map system to solve these sort of equations. And I mean, it's fairly simple. I mean, I have examples upon examples of obscure equation that you don't normally ever will see, but I'm just trying to make it complicated so that it just to prove to you that it works, right? So now we got that done. Let's look at the chain rule. Okay, now chain rule is a very important topic, not just to feel like I've said this before, but it's a very important topic because not only to deep learning, but it applies to many facets of physics, right? Now, my background is in mechanical engineering, and I specialized in geothermal engineering, which is basically, it's kind of like the same as oil and gas, but except we're not mining for oil, we're actually mining for heat, right? And of course, there's a lot of physics involved, and most of the times with we describe things using derivatives and also the chain rule. Why chain rule is important? Chain rule is important is because you can rate in a more sensible a way that makes sense. Okay, so I'm not sure what I just said makes sense, but just it's talking out of my head right now. So chain rule. Now chain rule is simply, I'm not sure why it's even a thing. It's so simple. So for instance, right? Let me give you a problem, and then you'll appreciate what chain rule is. Okay. So now this what is it? Okay, this problem illustrates what chain rule is, like almost perfectly. Okay, so without knowing anything about chain rule, I think it's the best moment for you to absorb what actually chain rule is. Okay, now so for example, we have a wall here. Okay, I just pretend this is a wall. Okay, now you have a broom or a stick or whatever that is. Okay, and this thing here is falling. Okay, now it's falling at a rate of say 5 miles per. So it's falling pretty quickly. Okay, 5 meters per second. Sorry, not miles, meters. So it's falling pretty quickly. And then okay, so this end here is falling. Now you might be confused at what does this mean? Okay, this is a time rate. Okay, so if you look at a coordinate system, so you have x to the dot. That means it's a time rate, which basically means is something per second. Okay, it's always per a unit time. Okay, it could be per minute, per hour, per decade, per year, or whatever. It's a rate that is it is a time rate. Okay, so let me erase that. Oh, by the way, I should really explain to you some of the um, what you call it, the conventions of the calculus language. Okay, so this x dot here, I can write that as dx over dt. Okay, now what does this mean? This means that I have a variable x and I have a variable time. Okay, now this tells you is, okay, what is the rate of change of x respected to time? Okay, so how would x change if time changes? Okay, now it makes perfect sense, because if I say, hey, this is 5 meters per second. Okay, so x, the way x would change if time change is 5 meters per second. Makes perfect sense, right? Because as a unit of time change, x would change by 5 meters. Okay, so dx over dt, what it means is you have a distance, you have a time. What would how would time how would distance change if time change? Okay, well, it's 5 meters per second. Uh, Fairly simple. Okay, so now the reason why people write this is just because that we are lazy. We don't want to write this whole thing out. X dot, you know, it's basically a convention in physics, right? So let's go back to the question on hand. So you got this thing right here. Okay, now the question is, what is the rate of at which this is falling? Okay, which is what? Which is the y dot. Okay, so we have this, and we want to find this. Okay, so let's write this thing down. So you have dx, dy over dt, right? This is what we want. Now let's look at what we have so far. Okay, so we have dx over dt. Huh. That is really interesting, because what can we do to this? Or should I put it, what should we multiply this by so that we can get dx over dt? Sorry, dy over dt. If we just look at this part right here, right? Basically, what we want to do is we want to get rid of the x and somehow put a y in there, right? So to do that, actually, you have to multiply by dy over dx. Now, this whole thing, this whole thought process that I've just done, that's the chain rule. Okay, that is the chain rule. It is simply multiplying two different rates together to get what you want. That's the chain rule, guys. So the reason why this works is because the dx and the dx. Let me switch colors here. So dx and dx, they cancel each other out. So dy will jump into here and becomes dy over dt. So the question now, so basically, you know, doing the chain rule helps you in finding what you need to know. Excuse me. So the chain rule says to me that if you want to reach dy dt, you actually need to solve what's dy dx. Okay, now if this is a straight stick, which I don't know why it wouldn't be, and this is a right angle, well, this is actually a triangle problem, right? So you have y and you have x here. Okay, so I have the relationship. Well, actually, how can I relate y and x together? Well, using the Pythagorean, I can't remember, but you know, it's that, you know, x squared plus y squared equals c squared, where c is a constant, right? This is my c. So how do you actually derive this, though? I mean, it doesn't look like anything from the map system. That's because this is a implicit formula equation. There are two different types of uh, expressions to a um, what do you call it, to a formula. Okay, one is explicit, one is implicit. Now what we're dealing with here, that's a implicit uh, equation, which means that it doesn't tell you what y or x equals to. So an example of an explicit formula would be y equals mx plus c, because I'm explicitly excuse me, because I'm explicitly telling you that, hey, y, this variable y is equals to mx plus c. But here, because we have x squared plus y squared equals c squared, I'm not really actually telling you what x and what y is. So in this case, if you want to differentiate this, what you actually need to do is use a thing called an implicit differentiation. Okay, so basically what you want to do is you differentiate this whole thing with respect to x, because look, this is my dx, right? Now dy here is just basically a equation. So I can write d over dx of x squared plus y equals to c. Now, I don't really care about this part because c is a constant. So anything if you derive anything with a constant, that will become 0. So I don't even really care about this side. So let's look into this. So so I can write this as d over dx of x squared plus d over dy squared equals 0. Okay. Now this is very simple. Now I have I should really back up to this for a minute. Now, what have I just done here? Why is it different from anything that we've done before, right? We have dy dt, we have dx dt, we have dy dx, but what is d over dx? Now, one thing you have to understand is we are differentiating we're differentiating something in respect to another variable. Now, this thing can be a equation, right? So let's say I don't know. Let's say that y is equals to, I don't know, t squared or t cubed plus maybe t cubed, right? So I can actually write this and say, hey, dt over dt, d over dt of t cubed, that's equals to 3t squared. This thing and this is equivalent. This is just a shorthand of writing this instead of that. Okay, so I hope you guys can see the difference, and I hope that this right here makes sense, because right here what I'm just trying to do is differentiating each of these in respect to y, in respect to x. This, so just made a typo, so this is x right here. Okay, so anything that you differentiate in respect to, that variable has to match, right? So x and x, they match, so I can comfortably differentiate that. So okay, so it's 2x. Now let's look at this one. X and y, they're different, right? So let's think about this. If I really want to differentiate that, what should this be? This should really be a y, right? So okay, so let's assume that. So dy over d over dy of y squared. Hey, everybody's happy, like I have y and I have y here, I can differentiate that. But it's not really the case, because of what I'm saying here, hey, I want dx though, not dy. So what I can do here is use the chain rule. So if I want to make this into an x, I will actually have to cancel out the dy and put back in the dx. You see what I did? Dy, they cancel out, and this gets put back, right, equals 0. So 2x plus, now this is 2y of dy dx equals 0. So actually, so if you rearrange that, you can actually go dy over dx is equals to a negative x over y, which makes perfect sense because if I write this back here, dy, excuse me, over is equals to negative x squared plus divided by y. You can see that if x is positive, then the movement of y is going to be a negative because it's given by this. So it's opposite, okay? So let's bring this all back. So you got dy over dt is equals to dx over dt multiplied by negative dy over dx. Now, this is the dx over dt, that's 3, right? So negative 3x over y. Now, this is something that is very interesting, and it is what calculus can teach you, is that, hey, the dy over dt thing right here is given by both the distance of the length of x and y. So you know, it's just simply multiplying the rate of dx dt over dy dx. This whole thought process right here, that's the chain rule, okay? It is simply finding out what you have, what you need. So this is what you have, you know, and this is what you need. And this is what you need to find out, okay? So that's the chain rule, okay? It doesn't really get more complicated than this. It's just simply finding out, okay, so let's go back to this, right? So I want dy right here, right? So I need to put a dx at a denominator to cancel this out and bring the dy back in. Same goes here. This is the implicit differentiation. Implicit, I can't spell implicit differentiation. Okay, so this is the implicit differentiation. Yeah, so hope you guys find this useful. If not, I mean, if you have any other questions, of course you can just, you know, hit me up on Slack or drop me an email. I don't care. I'm always, you know, up for helping other people getting into this. So, what is our next topic? Our next topic is matrix multiplication. Now, the way I want to teach this is I want to relate this to the MLP because it's very matrix heavy. That's what I think. And I think that designing the architecture really depends on you knowing, you know, just matrix in general. Okay, so matrix is nothing more than just a group of numbers arranged in a grid. Okay, might not be too technical, but essentially that's what they are. So matrix multiplication. Okay, so one golden rule that you need to know is, before I even jump into what matrix is, if you have one matrix, let's call this matrix 1, okay? If you want to multiply this by another matrix, one thing that you really need to check, okay? So with matrix, you have dimensions, right? So let's assume that this is a 2D matrix. So you got the row, and the height. The row and the column. Excuse me, let me rewrite this. Now, the reason why I want to subscript this is that I wanted to note that this is the matrix 1. Another one here is 2 and then n2. Now, one thing that needs to match, which is n1 must equals to m2. That's all you need to understand matrix multiplication. Okay, the actual multiplication, you know, how Pytorch does things, doesn't really matter to me, because you're not really concerned about this kind of a low level operation. I mean, and you know, there are a lot of other what is it? You know, YouTube videos that teaches you how to multiply matrix together. So I'm not even going into that. But in designing, you know, MLPs, you know, you have MLP, you have. Oh, let me just write this whole thing. Eraser. So I have more room to write on. So in a certain NLP, now let's just go back to, you know, the MNIST. Okay, so let's start with the MNIST, right? So there's one thing about matrix multiplication that you really need to understand is, so for example, if you have two matrices, right? Now, I don't care what's inside of it. All I'm caring about is the dimensions of these two matrices. So if I denote this as M1, N1, and this is M2 and N2, if I ever want to multiply these two together, the N, so the N1 must equals to the M2, okay? And that's all you need to know. You don't really need to know the actual how things are multiplied together, because quite frankly, you don't really need to know. Pytorch does everything for you. So you don't really need to concern yourself with that, because that's kind of low level stuff. Low level as being, you don't want to get caught up on trying to understand how things are multiplied, because that's not really the key issue here. So all you need to understand is the column of the first matrix has to equals to the row of the second matrix. So let's say right now I'm going to design a model that will detect the MNIST. Now I'm gonna pretty much copy what the Udacity people taught, which is you basically take a sample, right? So the sample of one sample, you have 28 by 28 pixels, right? So that is equals to 784 of pixels. Now, basically what this is doing is that, well, a computer, how computer sees an image is basically vector. They are represented in a matrix form. Okay, so if we want to design a MLP, MLP only takes in vectors. Okay, so this has to be a vector form. You cannot feed just the image into an NLP unless you can somehow compress it into a vector form. Okay, so you do all of that, and then that's number you arrive to. Okay, so the 784 pixels vector is exactly the same as, has the exact same information as the 28 by 28 pixel image, right? So if I were to just design this, right? So right off the bat, I would know that. Let me actually delete all of this stuff. Okay, so I have, recall 28 times 28, that's equal to 784, okay? So 784, right? So that would tell me that my input layer has to be the nodes, right? Each of these nodes, you have 784 nodes. Okay, now right off the bat to here, you have this thing called hidden layer. Whatever that separates between the hidden layer and the output layer, that's the hidden layer, right? So you have this big, not big, but uh, hidden layer that's sitting between the input and the output, right? So we all know what the output is, right? Because how many classes are in this? Well, there's 10. So you have 10 nodes for the output. The reason why we have 784 as the input is because that's pretty much constraint to us. So because we have 28 by 28 sized samples, right? So, but because NLP can't take in matrices, we're forced to downgrade this or downsize this, or actually manipulate this to a vector form. So the 28 by 28 pixel image has the same information as a 1 by 784 pixel information. So they contain the same information is what I'm trying to say. So you have the hidden layer right here, right? So let's say I have two hidden layers, right? I have one hidden layer that's right here, and then this will get transformed into another hidden layer. Okay, now how do you determine how many layers you have? Well, it's up to you. There's no golden rules as to how many you want to put in or how many there are sufficient. But you should always do your research. I mean, Google nowadays, it's you find anything on Google, right? So find papers that matches with what you're trying to do, and then go from there. Now, what about how many nodes, right? So from what I heard, what I learned from my research is the more nodes that you put in, you are forcing the model to detect more subtle features, right? So, for instance, if you have just two nodes right here, right? Basically, what you're saying to the model is, I want to detect just two major features of my image, and if you have 200 and I don't know 65 or something, that means you want the model to detect more subtle and sophisticated, not sophisticated, but more patterns in your image, right? So let's get back to this. So let's say I have 606. Sorry, I cannot think. Excuse me. So 265. Okay. Now let's say I want to. Well, let's do this. Let's do this. Sorry, guys. I'm gonna match with what I wrote here. So 128, and then you have 64. So so I went out to the outside world and read some papers, and these are the two numbers that I want. Okay, now to transform what you have into this matrix, you actually have a weight matrices here. So in order to transform from 784 to 128, you actually need to multiply this by a weight vector. Sorry, a weight matrix. Same goes to here. Excuse me. And then another weight matrix here. So designing, W1, W2, W3, that's the essential part of designing a model. Is you're not really designing the input, you're not really designing the output, you're not really designing the hidden layer too, because, well, you actually are, but you should really follow what research are telling you. The only thing that you are actually designing is the W1, W2, W3, right? Finding the right dimensions that links everything together, okay? So let's put this back into perspective. Okay, so let's look into this. So let's say I have a batch size of 10, right? So 10, well, let's say it's 20, okay? Because 10 and 10 is the same number, so I want to use different numbers. So 20, and I have a feature of 784, right? So 784 would be my input to this whole model, okay? So let's think about this, right? So you have 20, 780, come on, 784 going into this. Now, now, the transformation that needs to happen is I need to transform this to a 128, right? Because it's a vector. I want to times this with a matrix that will give me 20 by 128, right? So I actually need to multiply this by actually okay. Okay, so let's put everything into perspective, okay? So what we have here is a MNIST MLP model, okay? Now let's look at what is happening to the matrix if we run it through this model, okay? So let's say we have a batch size of 10, and then again we have a feature of 784. Okay, now as it passes through, now let me do this. So as it passes through here, right, you're going to multiply this with the matrix, and that matrix will time W1 will turn this into a 10 by 128. Okay, again, and then if you go back to here, so it comes out as this, and then it goes through another matrix multiplication. Okay, so it times another W2, and you will get a 10 by 64, and then you multiply this by a third matrix, which is it has to be 64, right? Oh, excuse me. It has to be let's see. Yes, it has to be 10 by 10. Okay, so this is what's going on throughout the multiplication. Now the question is, well, what is the dimensions of W1, W2, and W3? Now let's look into it. So for W1, let's just do this. So you have 10, and then 784, and then you multiply this by something, by something, and that will give you 10 by 128. Now, if you recall, any multiplication that needs to happen, the first row, the matrix of the first, the column of the first matrix has to equals to the row of the second matrix. So, given by that, what we can deduce is that W1 is actually equals to 784, comma 128, right? Now, what is the W2? W2 would be, now let's look at this. So you want to go from semicolon 10, 128 times something that will give you 10, 64. Okay, so Same rule applies. So W2 is equals to, this has to be in here, and then 64. And then same goes to W3. So W3 real quick. 64, it has to be 64. What is the output? Output is 10, so 64, 10. 10. Okay, now if we just quickly rewrite all of this, so we have this, we have this, and we have this. So let me rewrite all of this, okay, so it's easier to see. So 784, and then 128, and then we have 10. Oh, sorry, is it 10? No, it's let's see, 128, 64, and then 64, 10. Now, this is my architecture of my model. So if I say to you, hey, I have, I don't know, 33 samples, and of course I have 784 what is it, features. I'll multiply that. What does that give me? Well, that will give me that, and that pretty much cancels, and then you bring these two numbers together. So you have 33, 128, okay? And then you multiply this with this, what you'll get is 33, 128, and you multiply this with that, excuse me, so, no, sorry, that's 64. So multiply this with this, that will give you what, 33 of 10. Now, one important observation that you need to make is, you see how the batch size are preserved. Yeah. So basically, what NLP essentially is trying to do is it is trying to manipulate the features and reduce that to a class. You see what is happening? It's keep on reducing it. That's all it's doing. It is trying to deduce from the features to the corresponding class. Okay, and the way to do that is to manipulate all of these, right? So this is the architecture that you're trying to design, is to, what is the optimal excuse me, what is the optimal size, what is the optimal nodes for this, and for this. If you put in more nodes into this, you might slow the computation down. If you put more layers in, you might be more prone to overfitting, right? So I hope this basic tutorial will help you understand the inner workings of the MLPs in general. Okay, it is really just nothing more than multiplying matrices together and then reduce the features column to the corresponding classes. Now, we have one more topic, and that is slopes and gradients and slopes. Okay, I wish there's a way for me to just erase all of this, but couldn't find a way. Well, let's just leave it like this. Okay, so basically, real quick, slope and gradient. So let's go back to f of x. All right, so f of x is equals to 2x. Now, if you draw this on a a Cartesian coordinate, you'll get this, right? You don't really need to know where the shape comes from, but I'm telling you, it looks something like this. If you differentiate this, f prime x equals 2x. What does 2x mean? what does this thing mean? Well, it means that uh, it's not really that hard to explain, but I'm just having a difficult time trying to explain it. Basically, what it means is you can find the slope, the gradient, at any x value. So, for example, for instance, let's say this is x1, x2, and x3. Okay, now let me redraw this. Let me have a fatter one, so it's easier to explain. Okay, so what that tells you is, hey, if x is 1, so x1, so if x is 1, that would becomes 2. What this tells you is at x equals 1, the slope of that gradient is 2. If I say to you, hey, if f prime x of 2, well, that is equals to 4. So what that tells you is at x equals to 2, the gradient is actually equals to 4. That's basically all it's doing. Okay. The first derivative, which is the 1 prime, the one with the 1 prime, you can find it's basically a gradient equation of that equation, right? So basically, you can find any getting tired here, tired of thinking. Okay, anyways, you can find gradients on any point of x. So let's for instance, let's say this is another parabola, and let's say this is +1 or so. Oh, actually, that's the reason why you don't. So any derivative of a constant will be 0, because what this is saying is actually this, where this is 1. So you move this thing up by 1, but it doesn't really change the shape of the curve, right? So if you differentiate that, well, x basically turns to nothing. It's equals to 2x, which makes perfect sense because the gradient doesn't really affect, it's not affected by me moving the curve up by 1 unit, right? So same applies. You got 1, you got 2, you got 3, you got 4. So 1, so that will be 2. 2 will become 4. 3 will become 6. 4 will become 8, right? So basically, whenever you differentiate a equation, you're trying to find out what is the gradient function, right? Very simple. Now, there's one more topic that I want to cover, which is the cross entropy. Now, the cross entropy, it relates to well, actually, before I go into cross entropy, I wanted to explain to you what exactly is entropy. So entropy, I believe, first came from physics. Okay, from more precisely is from thermodynamics. So entropy, if you look in a system, right? Let's say you have an enclosed system. It's a closed system. Basically, in physics, what a closed system is that there is no external force or external energy that goes into this square box. Okay, so the entropy comes from, I believe, the first law or the zero, because it's so important. I think it's called the zeroth law of thermodynamics. Okay, the number doesn't really matter. All I'm trying to say is entropy in a closed system basically means that anything that's inside of the system will decay over time. Okay, now what is decay? If you have a perfectly arranged system, everything is neatly in place. So let's talk about, let's say it's some sort of a gas, right? So this gas is perfectly, it might be a really bad example, but just think of anything that can be organized in a neatly manner, okay? What entropy is that over time, this system will decay, which means that it will the structure integrity will degrade over time, which means that it will no longer be uniform. It will just degrade and things will be everywhere. Okay, now there are a couple of significance of this finding, right? The first what you call it, the first um, significance of this is that time is it, it, the first significance would be the uh, time can only travel in one direction, because if time were to reverse back, has the potential to reverse back, okay, you would have to input energy into the system and hope that the whatever that's inside will magically go back in time and then be whatever it is at time zero, which is impossible, right? Basically, what you're saying is that let's say here's you, right, and you're standing in a pond, right, and you drop a a rock into the pond, and then you have ripples going out, and then by you doing that, you're basically inputting energy into the pond, right? So let's say you have 5 joules, whatever the case may be, right? Now if you consider the earth itself as a closed system, which is not, but let's just assume that, basically if you were to, if time reversal is possible, it means that you can actually give you give uh, the pawn 5 joules of energy, and the rock will jump right back to you, and the ripple never happen, which is impossible, right? So that's one of the significant findings of the entropy. Now, second of all is, let's say you have your own room, right? Now, let's say you can even do this for an experiment. So it's a Sunday morning. You're getting ready for, I don't know, for work the next morning, and you want to neatly organize your room. So you put all your books here. You made your bed. You I don't know. You vacuum. You pick things up. You put things back where they used to be. Things like that. Now over time, if you don't put energy into it to actively keep things organized, everything will decay in your room. What that means is that things are not where they should be, and things like that, yada yada yada. So entropy is a measure of uh, disorder. Okay, is what I'm trying to say. Entropy is a measure of disorder. Um, so how does that fit into cross entropy then? Now, cross entropy is a very interesting subject, because it tells you, uh, let's just look at an example, right? So let's say you have a classification model, right? Now, I'm not gonna go into details into you know what how you do that, because it's in the lecture notes. But cross entropy, now let's say you have two models, right? The way you should think about cross entropy is this. If this gives you a cross entropy of, say, 5, and let's say this gives you a cross entropy of 0.8, you can think of that as saying, hey, this model has a lot of disorder, right? Now disorder or entropy, disorder and entropy is really saying that there are not enough, there are a lot of misinformation in this system. So if you say that if you put in a sample and it comes out to be like, it's a cat. So say, for example, it's a cat and dog classifier, right? And say if you put in an image of a dog and it comes out to be 68%, because the cross entropy is 5, basically you look at this number and you look at this number and you think to yourself, hey, it is telling me that it is most likely it's going to be a dog. But if I look at the cross entropy, you will think to yourself that there is a lot of misinformation here. There is a lot of chaotic things that are going on. Should I really trust this number? You know, and in fact, it is a dog though. But it's a dog. Is it because of this probability, or is it just because of random chance, right? So you should think to yourself, hey, 68%, is it really based on the probability, or is it really based on just pure luck, as opposed to this, a 0.8, which means that there are a lot of information in there. That's why it is not chaotic, okay? And then let's say if you predict that to be 68%, okay, it basically tells you that the probability of that sample is in fact a dog. It's not due to random chance. It is probably due to this being 68%. So I would trust more on the output rather than on pure luck. Does it make sense? So long story short, if you have a 0.8 as your cross entropy, it basically says that there are not chaotic. First of all, it's not chaotic. It is very neatly organized, and it is a score that you can trust. Okay, there are very little chance that this number, or excuse me, the classifying is not really based on chance. It is really based on this probability. As opposed to this, if you have a cross entropy of 5, there's a lot of chaotic stuff going on here that will cloud your judgment and say, hey, the classifier say it is 68, but should I really believe this, or is it just pure chance? This is dirty. This is very dirty, and this is very clean. It's a very dirty 68%. There's a very clean 68%. So you can think of that way. It is also a measure of error as well. But I just want to give you guys the definition of entropy. Entropy is a measure of disorder in physics, and you can think of it the same way in this application that we're doing right here. So I hope that you guys understand the second part, because I'm getting pretty tired. But yeah, if you have any questions at all, feel free to drop me a message, send me an email, whatever. We can even arrange a Zoom call for everybody, so I can teach everybody at once, so we don't have to do this video stuff. So thank you for tuning in, and I'll see you guys hopefully next time when I do more tutorial stuff. So thanks for watching, and